This video is going to look at how photoelectron spectroscopy data can help us inform the development of the shell model. So currently we have pictures like this, for example, for this atom neon. So what we notice about neon is that we have a plus 10 charge in the nucleus, then we have one shell with 2 electrons, these little red dots, and then an outer shell with 8 electrons. That accounts for all 10 electrons that neon has. We know that the first ionization energy from electron impact experiments is 2.08 megajoules per mole. So we might predict that the electrons in this atom occupy 2 energy levels, and that's shown on this energy level diagram here. So here the energy level 0, that's the energy when an electron has been completely removed from an atom. The electrons that are in this outer valence shell, they're going to have an energy of negative 2.08 megajoules per mole, and so I put 8 electrons at that energy level, indicated by these 8 red dots. Then these 2 electrons that are on the inner shell, the first shell, they're just 2 there, and they're going to be really close to this plus 10 charge, and so they're going to have a very low, very negative energy on our energy level diagram. So we would predict then, if we do a photoelectron spectrum, that we're going to get a peak at 2.08 megajoules per mole, corresponding to removing these electrons. And since there are 8 electrons in this level, we expect that the peak is going to generate more electrons, more intensity, and it will be roughly 8 units high, or 8 times higher than we might get if there were just a single electron here. Here at the really low energy, we would expect another peak. We don't know where it's going to occur, but some really high energy we would expect. And it would be corresponding to 2 units high. So this first peak right here would be 1/4 the height of this second peak. So that's our predicted photoelectron spectrum. Notice that I'm following the usual convention in photoelectron spectra of letting ionization increase from right to left. So high ionization energies are on the left here, and low ionization energies are on the right. That might kind of, you can think about our pictures, we start in the center and move out, we get to progressively lower ionization energies because it's progressively easier to take the electron off. Or correspondingly, we move to progressively higher energies as we approach 0. So let's see what the actual data looks like. So this is a sketch of what an actual low-resolution photoelectron spectrum might look like for the element neon. And here it is. So relative number of electrons, again, are plotted on the y-axis. Ionization energy plotted on the x-axis, but increasing from right to left. And then this little 2 little slash marks right here are indicating that we have a big change of scale. So if this were on a full graph paper, 84 would start over here and run for a long way with nothing interesting happening until we got to right here. So we've just snipped that center section out, and that's what these 2 little lines mean. So if we look at this peak, we look at this spectrum, we see that it has some similarities to our predicted spectrum. We have a tall peak, most of the electrons at 2.08 megajoules per mole, and that is as predicted. But there's a major difference, and that is that we have 3 peaks instead of 2. So now we have to figure out what electrons these correspond to. So it looks as though, if we were thinking about peak heights, that this last peak is about 3 times as tall as these other 2 peaks. So if we're thinking about relative peak heights, then this peak might have a height of 3, this peak would have a height of 1, and this peak would have a height of 1. So now we have to figure out where the electrons would go. So we know that the easiest electrons, the valence electrons, you pull those off at 2.08 megajoules per mole. So you remove the first electron, and that's the ionization energy for neon. So we'd expect that this peak out here corresponds to the valence electrons. This peak is the one that's at highest energy, so we would suspect that these correspond to the inner shell electrons, the ones closest to the nucleus. So some inner shell close to nucleus. The other thing we know about the inner shell is that we're kind of looking at our model and we're thinking that that's going to correspond to 2 electrons. we know that in neon there are a total of 10 electrons. If I just add up these peak heights, 1 plus 1 plus 3, then I don't get to 10, I only get to 5. So what I probably need to do is double these peak heights. So this peak probably corresponds to 2 electrons, this peak probably corresponds to 2 electrons, and this peak probably corresponds to 6 electrons, just based on the intensity of the signal. Alright, so then I've got a different picture now for my energy level. So let's draw an energy level diagram that's consistent with the observed photoelectron spectrum. So up here is 0 again when we've ionized the electron. So we've got an energy level here that is at negative 2.08 megajoules per mole. There's another energy level here at negative 4.68 megajoules per mole. And then way down here, really low in energy, there's another energy level at negative 84. And what we predict, based on the peak heights in our spectrum, one way to interpret this is to say that there are 2 electrons at this energy level, there are another 2 electrons at the negative 4.68 energy level, and that there's 6 electrons at the negative 2.08 energy level. So this is modifying our shell model picture a little bit. It still is consistent with saying that this is maybe the first shell. And so we have a choice when we get up here. We can either start saying that there are more shells up here, or what we traditionally do is we say that these represent subshells in the n equal 2 shell. So both of these together make the n equal 2 shell, and then these are subshells. So to keep track of them, we need labels. Right now our shells are labeled with numbers, so we need a way of labeling subshells. So we're going to say that the lowest energy subshell, the one that takes the most energy to remove an electron from, we're going to call that an S subshell. So we're just going to use a letter to label it. Now why don't we use a letter like A, B, C? Well, for historical reasons, we want it to agree with things that chemists had been doing before we've had these pictures, and so they started labeling things S and so on. So the next label is going to be P, and in order of energy then, so let's draw a little picture now that labels the energy order of the subshells. So going from low energy on the right to high energy on the left, the S subshells have the highest energy, and then after that, P subshells have the next highest energy, then it's D, and then it's F, and then it's G, and from then on it would be alphabetical with our labeling scheme. So again, these labels S, P, D, F, G, those just come from historical reasons. When chemists used to look at a different kind of spectra, they used to look at emission lines from atoms, and some of those lines had different characteristics, like S stood for sharp, and P for principal, D for diffuse if you had a fuzzy line. If you had a really thin line that was really close to another line, we called those fine. And so that's where these letters came from. So we're going to use those to designate our shells. So this shell, since there's only one subshell, we're going to call it the 1s energy level. And this energy level right here then, since it's in the n equal 2 shell, we're going to call it the 2s subshell. And up here, since we're still in the n equal 2 shell, these two energies are pretty close together and very far away from this energy. So we're going to make them still the same shell, and we're going to call this one the n equal 2 shell, but the p subshell within that shell. So we've got 1s, 2s, and 2p. To make this notation a little bit easier to keep track of so I don't have to draw a picture like this, chemists have adopted a shorthand notation, something called an electron configuration. An electron configuration is just a shorthand summary of how many electrons we have in each sublevel. And so normally we will start labeling the subshells in order from low energy to high energy, although sometimes we list them in the order in which they are filled. We'll talk about that later. So the electron configuration, 1s, in that subshell, we've got 2 electrons, these two guys right here. So we're going to call it 1s. We're going to make a little superscript 2 up there. Right? So we're not squaring the s, this just means that there are 2 electrons in that 1s subshell. The next subshell we come to is the 2s, and again there are 2 electrons there. And then the next subshell that we come to is the 2p, and looking at this, there are 6 electrons. All right, so where did all this come from? Again, this just comes from interpreting the photoelectron spectrum and thinking about the energies and what these relative heights are telling us. So our picture now is going to have to be modified a little bit. And so how might we represent this picture? Well, we still have a +10 charge in the nucleus. So there's our nucleus. We still have a first subshell, that's our 1s subshell now, which still has 2 electrons in it. Then much further away, we've got the 2 subshell. And so what I'm going to draw to kind of imitate our pictures, I'm going to draw 2 rings, that are really close together. So this is the n=2 shell. And in this first shell, the s subshell, there are 2 electrons. And then in the 2p subshell, there would be 6 electrons for neon. And so maybe our picture would look a little bit like this for the shell model. So we've got an inner shell, then an outer shell, and this outer shell we can divide into 2 subshells. So that would be the picture for neon. So of course we can take different photoelectron spectra of different atoms of different elements. And when we do, we'll get different pictures. But for comparison, let's look at the energy level diagrams that would come from the photoelectron spectra of helium, neon, and argon, just so we can compare them. So again, we look at this photoelectron spectrum that's right here for neon, and from that we can figure out an energy level diagram that looks like this picture. So what we're going to do is draw, not exactly to scale, but the energy level diagrams for 3 atoms. So let's draw those. Based on their photoelectron spectra, here are the energy level diagrams for helium, neon that we just looked at, and argon. So there are a couple things that we notice here. So first off, the 1s subshell, as we go from helium to neon to argon, gets progressively lower in energy, much more negative. So looking here at argon, it's a whopping -309 megajoules per mole. And that makes sense because what we're doing is that 1s subshell is really close to the nucleus, but we're really increasing the positive nuclear charge because these atoms all have very different numbers of protons in the nucleus. The other thing that we notice is it appears that after we have added 2 electrons into an s subshell, that we start adding them to another subshell. So our guess might be that s subshells can hold a maximum of 2 electrons. Also, we see that the 2p subshell here in argon holds 6 electrons, just like it did in neon, but then we go up and start filling the 3s, which is at a much higher energy of -2.83 as compared to this lower energy of -24. So it seems like the p subshells can hold a total of 6 electrons each. And we see that by looking at this picture. So notice that the 1s continues to go down in energy, the 2s and 2p go down in energy as you're adding more protons, and then we start adding more energy levels up here. So we move from filling in the 2p to the third shell, and we start filling the s and the p's. So if we wanted to, we could write down electron configurations for all of these atoms. So this one would be 1s2. Neon, we've already done that, 1s2, 2s2, 2p6. And those are all superscripts, the 2, the 2, the 6. And now let's do argon. So we'll do argon down here. So we start off, going to go from low energy to high energy. 1s2, there are 2 electrons there. 2s, again, 2 electrons there, 1, 2. Then we come to the 2p next, and there's 6 electrons there, 1, 2, 3, 4, 5, 6. Next we come to the 3s, and again there are 2 electrons. And then finally the 3p, and there's 6 electrons there. So an electron configuration is just a shorthand way of summarizing the information that's in this energy level diagram picture, but without all these energies. So it's much more qualitative, but it tells us how many electrons are in each energy level. So using this information for argon, let's prove that we know how to understand photoelectron spectra and try and draw the corresponding photoelectron spectrum for argon. So let's get rid of this stuff that's over here on the left-hand side of my screen. So I'll just go in and erase that for you. And there we go, boom. So let's draw our photoelectron spectrum. So we're going to label our axes first. The y-axis is relative, so I'll abbreviate that rel, number, hashtag of electrons. Here we've got ionization energy, and we're going to follow the trend where it increases from right to left, and this will be in units of megajoules per mole. Okay, so we want to draw out our peaks. So the peak that's at highest ionization energy is the 1s. So I'm going to draw a little peak, and it needs to be 2 units high. So there we go. I'm going to draw a little tick mark there. And we're going to say that that's at -309. Actually, since these are ionization energies, this is going to be positive because that's how much energy we've had to put in to ionize those electrons. All right, then I'm going to draw one of these slashes to indicate that the scale has changed. And now we're going to draw another peak corresponding to the 2s. It's also 2 units high, so I need to draw it the same height as this first peak right here. All right, draw another tick mark there, and that's at 31.5. And then nearby, a little bit higher, I need to draw a peak that has 6 electrons in it. So if this one has 2, 6 is 3 times as high, 3 times as many electrons, so I need to draw it 3 times as high. So I'll do that. There's 1 time as high, 2, 3. There we go, that looks about right. So I'll draw a little tick mark there, and that's at 24.1. Alright, so then there's a big change in energy, big change in scale, so I'm going to draw one of those double slashes to indicate that we've changed the scale a lot. And then I come to the 3s electrons, and so again I'm going to draw a peak that is 2 units high, so right there, and that occurs at 2.83 megajoules per mole. And then another peak nearby that is 3 times as tall as that peak that I just drew, and that's going to be at 1.52 megajoules per mole. Alright, so this would correspond to the 1s, and again there would be 2 electrons there, the 2s with 2 electrons, the 2p with 6 electrons, the 3s with 2 electrons, and the 3p. So this would be the n equal 1 shell. Taken together, these two pieces would be the n equal 2 shell. Then there's a big break in energy, and taken together, this would be the n equal 3 shell. And so that's how photoelectron spectra help us think about the structure of atoms. And we've had to change our picture a little bit, modify it in the face of this new data, right? So we didn't know that we needed to split a shell into subshells until we saw this data. We also didn't know anything about how many electrons each of these subshells could hold, but now we can kind of generalize some of our data to figure that out. Let's continue looking at photoelectron spectral data for various elements. So here they are kind of shown, here are several different photoelectron spectra kind of shown on top of each other for different elements. So here's hydrogen, helium, lithium, beryllium, and boron. Then over here we've got carbon, oxygen, and neon. So based on these photoelectron spectra, let's try to write down what the electron configuration would be. So hydrogen, we've already done that one. We know it starts at the n equal 1 shell, and there's only one subshell, the s subshell, and then hydrogen just has 1 electron. So we're going to put it there. If we look at the data for helium, it appears that this peak is about twice as high as this peak. That corresponds to having a 1s2 electron configuration. Now with lithium here, we've got a peak that's about twice as high as this peak, and they're separated by a lot of energy. So we're going to think that the 1s level is filled, and that we start filling the 2s level with just 1 electron, because this peak is only half as high as this peak. Moving on to beryllium, the next element, we've got 4 electrons. The peaks are equally high, but they're separated by a big distance in energy, so the first peak is the 1s peak with 2 electrons, and the second peak is going to be the 2s peak with 2 electrons. Then we've got boron, and so we've got 1s. Remember, the s can only hold 2 electrons. Then we move way up in energy, so next we're at the 2s, and this first peak is twice as high as the second peak, so that corresponds to 2 electrons. And then this peak, well, since the s is filled with already 2 electrons, we're going to start putting in the 2p's. This would be 2p1. Then if we look at carbon here, we've got 3 peaks. The first peak is separated by a big distance from the second 2 peaks, and all the peaks are the same height. So that might mean 2 electrons in each one. So 1s2, 2s2, 2p2 would correspond to all 6 electrons in carbon. Then if we look at oxygen, so oxygen and carbon, oxygen is not the next element after carbon, right? But we're going to look at it next. So in between carbon and oxygen there's nitrogen here, which we're not going to look at. In between oxygen and neon there's fluorine. So oxygen has a 1s2, 2s, and then this peak is the same height, so that's going to get 2s2. And this peak looks like it's about twice as high as that peak. So what's it going to be? 2p4. Yeah. So knowing that nitrogen has one less electron than oxygen and one more electron than carbon, let's see if we could guess what the electron configuration for nitrogen would be. Well, following this pattern, it looks like it's probably going to be 1s2, 2s2, and then 2p. So we had 2p2 for carbon, we have 2p4 for oxygen, so it's likely that nitrogen's going to be 2p3. And what would that spectrum look like? Well, we'd have a peak that's this high. It'd be further this way, right? Then we'd have another peak that's also that high. And then this next peak would be one more unit higher. So if that's 2 units, then we go up 3 units like that. So maybe that's not quite twice as high, right? Just a little bit higher for 3. Then we'd have 4 down here. All right, so it might look like something like that. And then when we get down here to neon, we've already done neon, 1s2, 2s2, and then this peak is 3 times the height of this peak, right? 1, 2, 3. We divide it sort of into 3 segments with our eye, and so that would correspond to 2p6. And so what's the electron configuration for fluorine going to be? Well, following the pattern, 1s2, 2s2, 2p, and then we would have between 4 and 6, 5. So now we've written down electron configurations, like what the electrons are doing for all the atoms in the first and second row of the periodic table. And you see that there are some patterns that the photoelectron spectral data is showing us. Now let's look at some data for the third row of the periodic table, beginning with sodium. So the sodium photoelectron spectra, let me tell you what this table is about. So this table shows ionization energies for gas phase atoms of elements 11 through 21. So that's looking at the third row and a little bit on the fourth row of the periodic table. So we're kind of going to go through and see if there's some patterns. So what's being shown from the photoelectron spectra are the energies at which these different peaks occur. And we've also labeled them according to their shell and subshell. So these are the ionization energies in megajoules per mole. So what we see is that sodium has 4 peaks, 1, 2, 3, 4 peaks, and this last peak is only 1 unit high. So that's going to correspond to sodium having an electron configuration that looks like 1s2, 2s2, 2p6. So that's neon, right? The same electron configuration as neon. And then we go to the 3s shell, and since the peak is only 1 unit high, it's going to get a 1 superscript. So that last electron, that last valence electron, goes into 3s1 subshell, the 3s subshell, 1 electron, and it's going to have an ionization energy of 0.5 megajoules per mole. So magnesium also has 4 peaks, but the last peak is 2 units high. So it's going to correspond to an electron configuration of 1s2, 2s2, 2p6, 3s2 now. Then aluminum, we have the last peak is occurring at 0.5 megajoules per mole, and we have 5 peaks, 1, 2, 3, 4, 5 at these 5 different energies. And that last peak is only going to be 1 unit high in the photoelectron spectrum. So that's going to correspond to the same electron configuration that we've already seen, 1s2, 2s2, 2p6, 3s2. So that's based on the peak heights and these 4 energies. Now there's a 5th energy at 0.58, so we're going to put that in a new subshell, 3p. And since it's only 1 unit high, we're just going to put a little superscript 1, because there's 1 electron in that shell. Then if we look at the next elements, silicon, phosphorus, sulfur, chlorine, and argon, we've already seen the electron configuration for argon, so let's go ahead and complete these and just write out these electron configurations, and you can probably see the pattern. Okay, so I've drawn some lines to help point to which element we're talking about. So you see that as we move from aluminum to argon, that all we're doing is adding a little bit of height to that last peak, which corresponds to putting 1 more electron in the 3p subshell until we get up to 6. Now we are to the element potassium. So now we're starting on a new row, a new period of the periodic table, and now we've got 1, 2, 3, 4, 5, 6 peaks. So there's a last peak at 0.42 megajoules per mole. And that peak in the photoelectron spectrum is only 1 unit high. So we would write the electron configuration for potassium like this: 1s2, 2s2, 2p6. And again, these all come from looking at the number of peaks that we have, and those little superscripts here are relative peak height, okay, to account for all the electrons. 3s2, 3p6. For the next shell that we come to is going to be the 4s shell, and we have just 1 electron, of course at 0.42 megajoules per mole, corresponding to 1 unit high. Calcium comes next. It's also got 5 peaks: 1s2, 2s2, 2p6, 3s2, 3p6, and this last peak at 0.59 megajoules per mole is 2 units high, so we're going to say that that's a 4s2. Now things get interesting when we get to scandium. So scandium is the first transition metal, and you'll notice that we've added an extra peak. So it has 1, 2, 3, 4, 5, 6, 7 peaks in it. And let's just look at what the photoelectron spectrum for scandium might look like based on that data. So I'm going to scroll down so that we can still see the data for scandium. We're going to write out its electron configuration here. But first, let's draw in the photoelectron spectrum. So I'm going to do that real quickly here. So here's our photoelectron spectrum. And it agrees with what we would expect, right? 1s2, 2s2, 2p6, because this peak is 3 times as high as this peak. Then we've got 3s2, and then 3p6. And then up here in energy, we've got these 2 little peaks. So this peak is kind of consistent with the last peak that we were looking at in calcium was 0.59, and it had 2 electrons in it, and it has now moved to 0.63 in energy, so that's a little bit higher energy than what we saw for calcium, and it's still got 2 units of height, the same as all of these. So that's consistent with it still being a superscript 2 up there, and it's kind of consistent with it being a 4s, right? So that's where we had the electrons for calcium, and we had 2 electrons there, and we know that when we put 2 electrons in an s subshell that it's filled. So the question is, what do we do with this last peak that's here? Well, it's a peak that is higher in energy than the 4s subshell, so that means that it is somehow on average closer to the nucleus, that shell is closer to the nucleus. So it makes sense perhaps to group it in, and it's not all that far away perhaps from the 3s here, to group it in with the 3s. And so that's what we chemists do. So we're going to say that this little shell right here is part of the n equal 3 shell, and so we've got to give another subshell label to it. And you'll remember next in our funny little alphabetical code we had S, P, D, and so D comes next in our labeling scheme. So this is a 3D1. And so the electron configuration for scandium we could write as 1s2, 2s2, 2p6, 3s2, 3p6, then 3d1, 4s2. So this electron configuration written this way shows the shells in order of energy, from high energy down here to low energy up here. So these low energy electrons are going to be the easy ones to remove. So if we try to remove an electron from scandium, we're going to remove these 4s electrons first, because they're the ones that are lowest in energy. It only takes 0.63 megajoules as opposed to 0.77. The other thing that you notice about these two is that these two energies are actually really close together. There's very little difference between 0.77 and 0.63. Sometimes you will see electron configurations written in sort of the order in which the electrons seem to be filling. So if we look at this pattern, it looks like we start filling 4s before we fill 3d. So sometimes you will see people write electron configurations in what we call filling order. So 1s2, 2s2, 2p6, 3s2, 3p6, and then next when we were filling potassium and calcium, we were filling the 4s. So we started putting electrons there before we put electrons in the 3d. So it'd be 4s2, 3d1, and that's in terms of when as we go stepping through the periodic table, we start putting electrons into a particular subshell. So you've seen that we started putting electrons in the 4s subshell before we started putting electrons in the 3d subshell. Then as we work our way across the transition metals, it's consistent with, you'll see this peak grow, and this peak stays about where it was most of the time. There are a few little places where this peak actually gets smaller and the 3D peak grows a little bit, but we will continue adding electrons to this 3D subshell. So by the time that we get to the last transition metal, zinc, we've got an electron configuration that looks like 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. And that's written in filling order. In in energy level order, we would have the 4s coming after the 3d, like we had up here in this case. This is also telling us that d subshells can hold a maximum of 10 electrons, because once we move from zinc to the next element on the periodic table, we start filling the 4p subshell. So you'll see that we have a peak that appears out here, higher in energy than the 4s, with only one unit of height on it. So it will be filling the 4p shell. So just as a summary, remember that the p shell can hold 6 electrons, and the s shell can hold, the s subshell can hold 2 electrons at most. So you stare at these numbers, we go from 2 to 6 to 10, you'll see that there's a pattern. So let's try and guess, if we were to have an atom that had some f subshells, how many electrons could the f subshell hold at most? Well, if this is 2 and going from 2 to 6, what do? We add 4. What do we do as we go from 6 to 10? We add 4. So what's our best guess as to the number of electrons that we might have in the f subshell? Yeah, we add 4, so we get 14 electrons. And that turns out to be correct based on the photoelectron spectral data for those lanthanide and actinide elements, where you start using these f subshells to put the electrons in. So it turns out that there is a pattern that is really pretty obvious when we go in and look at the periodic table and the electron configurations. And that's maybe not surprising, because we know that the periodic table is based on experimental data, and electron configuration must have a lot to do with how the elements behave.